Hello. I thought I'd do a couple short videos to help you with homework 4, which isn't due till April 10th, but I'm getting a couple questions about it. And these are questions I get every year, so I thought this is a great chance to highlight those a little bit. One of the questions you can see here on the screen, and that is about the friction coefficient associated with the hanging block problem. We hadn't, in the examples we did in class so far, I did not put friction in here. This problem does. So in order to do this problem, you actually have to go back to looking at all the forces acting on both of the blocks, and you have to include the friction force in order to really solve this problem. So the first question is this one here, returning to the original case, we have a 5 kilogram block sitting on the table and a hanging mass of 1 kilogram. It asks, what is the cutoff value for the static coefficient of friction that will not allow motion? And keep in mind that if there were no friction here, there would necessarily be an acceleration that way because there's only one force pulling on the block in that direction, that's the tension. So that's going to be the net force, it's going to be non-zero, the block is going to slide in this situation here. However, with friction, in this case I'm going to say it's static friction because the block isn't sliding, that's the assumption. We want to know if there's a certain amount of static friction, then the force from this block is not going to be able to pull that block. But there's going to be a threshold at which, if the static friction is low enough, this block's force would be able to break that static friction force, resulting in the block sliding. We want to find what that is. So that's what this question is asking. So what we'll do here is I'll sketch all the forces acting on this block and on this block. Here we have gravity. We have tension force. Here we have tension force. We have static friction. I'll call this Fg2. I'll call this one Fg1. And I'll call this one Fn1. Those are all the forces going on here. So the ones of most interest are these two, as far as our problem goes here. When Ft minus Fs equals 0, the block won't slide. All right, Ft, we know how big that is because it's got to be equal to Fg over here. And these two Ft's have to be the same. So therefore, this Ft has to equal that Fg. What's that Fg? Well, it's mass 2, the hanging mass times gravity. So it's going to be equal to 10 newtons. All right, so therefore, Ft is going to be equal to 10 newtons here, assuming the object is stationary and not accelerating. That has to be the case. That all of these are going to be equal. So the static case here is actually relatively simple. There's no acceleration anywhere. So forces have to add up to 0. So I could say Ft minus Fs equals 0. That means that 10 minus Fs equals 0. Whoop. That means Fs equals 10 newtons. Okay, so that's how big the static friction force is. So then, what static friction coefficient will result in that maximum static friction force being 10 newtons? Because this is the maximum we're interested in here. I should have put max in all of these because we're interested in that cutoff, which is associated with the maximum static friction that can act. So Fs, darken my marker, Fs max, I should say. In general, Fs is less than or equal to us Fn. Remember, we want to find us, that's what we're looking for. Just going to erase this for the moment. And Fs max is equal to us Fn. Therefore, us equals, and I'll let you do the rest, but that's what we're looking for this problem. The coefficient of static friction that will result in this situation here is what we get by solving that. Hopefully that'll help you with that problem. The next problem that resulted in some questions is, what is the value of kinetic friction coefficient that would result in a constant velocity of the block once it has started to slide? Okay, this problem is going to look a lot like the last one. Why is that? Because of the word constant velocity. So it's going to slide at constant velocity. So the fact that it's moving means that we're going to be dealing with the kinetic friction, not the static friction. You can't have both of them at the same time. As soon as the object starts moving, static friction stops doing whatever it's doing and kinetic friction takes over. All right, so kinetic friction is the friction force that we're dealing with here. And the acceleration is zero because it's constant velocity. So what I can say, I'll go back to Newton's second law, which I didn't write in the last problem, although I should have. I should have said that. That's equal to zero because of constant velocity. All right, so we have that. And F net for this block here is Ft minus Fk. That's going to be equal to zero, so therefore I could say Ft equals Fk. And remember, and then of course, Ft is also equal to Fg too. So the only difference between this problem and the last problem is that instead of Fs, we now have Fk. Everything else is identical. So if the block were to slide with a constant velocity, you now have the way to calculate the kinetic friction coefficient. Do it the same way you calculated the static friction coefficient for the case where the block wouldn't slide at all. Okay, this is a different situation, clearly, and I know that students have gotten confused. How could it do both? This is a different situation than the part A problem the previous problem we did a minute or two ago in this video. But you solve it the same way. All right? Then the last part of this problem that has caused questions in the past is, what is the value of the kinetic friction coefficient that will result in an acceleration of 0.1 meters per second squared once the block is started to slide? It's the very last part. All right, so for this case, I am going to erase everything here. All right, so I'm going to apply Newton's second law to both this block and this block. The only difference between this and what I did in class or in the video last week where I derived the hanging block acceleration is that I now have this friction term here of Fk. And now the difference between the constant velocity case in this is that I now have an acceleration, which the problem gives us is 0.1 meters per second squared. So what do I do here? I write out F net in terms of the two forces that are acting on the block on the table. Ft is to the right, so it's positive. Fk is to the left, so it's negative. I plug in Fk here. Fk is, the definition of Fk is, of course, mu k Fn. That is the definition of the kinetic friction. So I plug that in here, I substitute it. And that's equal to m1a, where m1 is that block's mass, 5 kilograms, times the acceleration of that block in that direction, which is going to be 0.1 meters per second squared. But I like to wait till the end to substitute all the numbers in. Then I know that Fn over here is equal to Fg1, which is equal to m1 times g. So I just substitute Fn with m1 times g. And this is my full equation for this side here. I do the same for the hanging block over here. And again, I have to take minus a as my acceleration because it's going to be accelerating down. Ft is my upward force. Fg2 is my downward force. That, of course, is going to be equal to minus m2 times g. That's going to be equal to minus m2 times a. So now I have two equations, two unknowns. I'm interested in calculating the coefficient of kinetic friction. So what I can do now is I would substitute this. I'd solve this for Ft, plug that into here, just like I did in the video the other day without friction, and solve this equation for mu k. That's the steps I would take in doing this problem. I want to leave the rest to you. I think you can do it at this point now that I've set it up. But all I'm doing is applying Newton's second law and then solving for what I'm looking for. Okay.